Right, I'm going to go over problem number 6 from the back of your review. It says the current in the ocean is 4 miles per hour at an angle of 15 degrees from the shore. Jenny's swimming at a speed of 12 miles per hour at an angle of 100 degrees to the shore. How fast is she actually moving and in what direction? So what's important to notice in this one is that for both the current vector and Jenny's swimming vector, the angle was given not with respect to each other, so not the angle between Jenny and the current, but both with respect to the shore, meaning some third reference point here. So when I see that, what we usually do is think of that shore, say, as the x-axis, and draw a picture of both of them with respect to the x-axis. So current is angle of 15 degrees, and it's 4 miles per hour. And then Jenny is at an angle of 100 degrees, and that's longer, so that's 12 miles per hour. That's 100 degrees. And so if both angles were given with reference to the shore, it's expected that your answer will be with reference to the shore. So what we're going to do is do everything with respect to the x-axis. In other words, divide them up into x and y components, so we get our component form with respect to the x-axis. So first thing we need to do then is find x and y components. So the current and Jenny. Remember that to find the x component, you always do the magnitude times cosine of theta, and to find the y component, it's always the magnitude times the sine of theta. So for the current, my x component would be for cosine 15, and my y component would be for sine 15. And then for Jenny, her magnitude was 12, and the angle was 100 degrees. So x equals 12 cosine 100, and y equals 12 sine 100. And I don't even need to type those in yet, because I know that for my resultant vector, the sum of those two forces combined, I can just, because the x's and y's are now all parallel vectors, I can just add the like components. So for my resultant, I can just add those up. The x component would be, let's just type that in the calculator, for cosine 15 plus 12 cosine 100 is let's just truncate that, 1.779. The y component would be for sine 15 plus 12, oops, forgot to close my parentheses, plus 12 sine 100. And so we will truncate that to 12.852. So what that means is I actually know where my resultant vector is now. I have it in component form, and that's where I say that r is the x component was 1.779. So to show that's in the x direction, I use vector I. And then my y component was 12.852. And to show that's the y direction, I use vector j. And then r is the sum of those two vectors. So what that means is, if I were to draw it, I go 1.779 over and 12.852 up. Oops, 852. And then r is the sum, meaning it goes from the beginning of that first vector to the end of the second. This is my resultant vector. And by the way, I should check against my picture that this makes sense. Notice if the current was pulling to the right and she was swimming to the left, my resultant ends up kind of somewhere in between those two. Also, the y component, since the y component in both of them was going up, I end up with a slightly bigger y component. So that works out. So now what I need to do, though, because what the question asked was not for the component form, but it said how fast is she moving and in what direction, meaning I need to find the actual magnitude of her speed and the direction or the angle. But that's easy, because now that I have it in component form, that makes a right triangle. So I'm basically finding the hypotenuse, which means I use the Pythagorean theorem. So to find my magnitude, I have 1.779 squared plus 12.852 squared. And so I just type that in, 1.779 plus 12.852 squared. And since that equals r squared, then I take the square root, and I get 12.852 2.974 as her total speed. So that would be the same units as the 4 and the 12 here, which is miles per hour. And by the way, if we want to be correct here, we write that magnitude with the absolute value bars. So I know how fast she's going now, slightly faster than she was swimming because the current was pushing her away from the shore a little bit as well. Now what I need to find is in what direction she ends up heading. So again, remember we were treating this as our shoreline. So here, if this is my shore, I need to find the angle with respect to the x-axis, which is usually what we're looking for. So here's my theta. Again, it's a right triangle though, so since I have the opposite and adjacent sides, or in other words, the y and the x coordinate, then I always use tangent. So tangent theta equals y over x, so the y was 12.852, the x was 1.779, and then of course to find theta I'd have to do inverse tangent to cancel that out. So inverse tangent on the other side. So in my calculator, inverse tangent of 12.852 divided by 1.779, and I get theta equals 82.119 degrees. And now remember with tangent, because there's two possibilities, you always have to double check your picture. But since I am in the first quadrant, somewhere between the 15 and the 100, that makes percent, so I don't have to add 180. So now I've got my magnitude and my direction, and I'm finished. I guess I should maybe add from the shore, since that's what my x-axis was representing. And then I'm done.